Welcome to this presentation in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, Associate Professor Emeritus of Electrical Engineering. It is my privilege to be your presenter today for a presentation entitled Bonus Circuits, Part 3, Don't Miss the Boat, where the acronym BOAT I made up, and it stands for the Beams Op-Amp Analysis Technique. Before I get into the heart of that, an update. Those of you who are curious about the whereabouts of the good and beneficent Mr. James, well, I had the privilege of meeting Mr. James for lunch on September 1st. In Urbana, Illinois. We spent a couple of very pleasant hours together, reliving old memories and reminding ourselves how we first bonded over a mutual interest in amateur radio at the University of Illinois over a half century ago. Hardly seems possible, but true. All right. I would like to announce the Beams Op-Amp Analysis Technique. It's a simple method for analyzing all sorts of op-amp circuits, but I've never seen it in a textbook. So this is why I have decided to name it after myself. Okay. Many op-amp circuits can be modeled with a single operational amplifier, an input voltage source, and two linear networks. These linear networks, which I've labeled A and B, take the voltage from the input and the voltage at the output and provide a linear combination to produce the voltages at, in the case of the A network, the non-inverting input, which I've labeled V sub P, and in the case of what I call the B network, it provides the voltage at the inverting input, which I've labeled V sub N. Okay, and the next principle I will use is the so-called virtual ground criterion. That is, if an op-amp is connected with a negative feedback path, it will move its output voltage in such a way as to reduce the input differential voltage, V sub P minus V sub N, to zero. Okay, it's called the virtual ground connection because in many applications, the non-inverting input is connected to a physical ground, and that causes a potential of 0 volts to appear at V sub N, but it is a virtual ground because that potential is not produced by a physical connection to ground, but through the op-amp circuit itself. So it's called a virtual ground. Okay, anyway. And if I combine these three relations, I get a simple expression for the transfer relationship of V out to Vn. It's A1 minus B1 over B2 minus A2. And this is it. This is the Beams op-amp analysis technique. It has an amazing range of applications. Let's apply it and see how it works. Here, let's take a simple voltage follower. Okay, in this case, V sub P is equal to V sub N. So the coefficient A1 is simply 1 and A2 is 0. Similarly, with the connection from the inverting input directly to the output, B1 is 0 and B2 is unity. And A1 minus B1 over B2 minus A2 gives us 1. A voltage follower, well-known circuit. Okay, that works. Now let's try an inverting amplifier. In this case, you see with the physical ground on the non-inverting input, then there is no connection from V in to the non-inverting input, and there's no connection from V out. So both A1 and A2 are 0. Now, B1, which we find by applying an input voltage V in and short-circuiting V out to ground and determining the voltage that appears at V sub N, well, that's going to be determined by V in and the voltage divider composed of Ri and Rf. So B1 is this value. And to find V2, we force V in to 0, and we force a voltage at VO and determine the voltage that appears at V sub N, and the ratio of Vn to VO with Vin set to 0 is coefficient B2. And from the voltage divider, we get simply Ri over Rf plus Ri, and then putting these coefficients into the BOAAT formula, we get V out to V in is A1 minus B1 divided by B2 minus A2, which is minus Rf over Ri. And again, another well-known result. Let's try a non-inverting amplifier. In this case, V in equals V sub P. So the coefficient A1 is 1. There's no connection from the non-inverting input to the output. So A2 is 0. And B1 now is 0. No connection from the B network consisting of this voltage divider to the input voltage. And B2 is determined by this voltage divider of RF and RI. And so V out to V in is A1, which is 1, minus B1, 0, divided by B2 minus A2. And 1 over B2 is simply RF plus RI over RI, which I can then divide through by RI, and I get 1 plus RF over RI, which is a well-known result for this amplifier topology. Let's try another one. This is a high-gain amplifier circuit, but one that does not require large resistor ratios. I can make an amplifier with, say, a gain of 50 out of this topology, but I'll need a resistor ratio of 49 to 1. If I'm designing with discrete resistors, that may not be a problem. But if I'm working with integrated resistors, then large resistor ratios are difficult to achieve. But this one allows me, this topology allows us to build a high-gain amplifier without using large resistor ratios. Let's see how it works. A1 is 1, A2 is 0, and B1 is 0. Now, to determine the coefficient B2, let's form, first of all, a Thevenin equivalent circuit from V out, RS, and RF1. And then if I replace this with a Thevenin equivalent resistance and voltage, I can calculate rather straightforwardly that V sub n is the Thevenin equivalent voltage multiplied by Ri divided by Ri plus Rf2 plus the Thevenin equivalent resistance, where the Thevenin equivalent voltage is VO times Rs divided by Rs plus Rf1, and the Thevenin equivalent resistance is Rs in parallel with Rf1. And making these substitutions into the expression for V sub n, we find that the coefficient B2 is this. And just like the example above, where we have 1 minus 0 in the numerator and B2 minus 0 in the denominator, V out to V in is simply the reciprocal of B2. So I just invert the numerator and denominator of B2 to get the final expression for the voltage gain. This circuit, with the resistor values shown, implements a voltage gain of about 131 volts per volt, but the resistor ratio does not exceed 10 to 1. Okay, and this is available to you as bonus circuit number 6. Okay, let's try another one. This is the so-called Howland Current Source, and this is one of those rare op-amp circuits in which the output of the circuit is not the output voltage of the op-amp. It is instead the current that flows through the load resistor. It is a voltage-controlled current source. Let's see, apply the BOAAT technique to it. Now, I'm going to set an initial restriction that R1 equals R2, R3, and R4. All 4 of these resistors are equal, and I'm going to call them simply R. The coefficient and let me explain, this voltage source here is actually not part of the circuit. It was something I added for simulation so that I could measure the output resistance of the current source. But for this analysis, this source it doesn't exist. It's set to 0. It's a short circuit. So ignore that voltage source behind the curtain. All right. So to determine A1, we apply a voltage Vin while VO is held to 0. And you see that V sub P is formed or determined from Vin by a voltage divider consisting of R3 in one branch, and the other is R4 in parallel with R sub L. Okay. And you'll notice that with R3 and R4 being the same, when we go to measure, well, when we go to determine A2, we'll put V into 0 and force a voltage at VO, and it's determined by a voltage divider formed of R4 in this branch and R3 and RL in that branch. But with R3 and R4 equal to each other, then the coefficients A1 and A2 are equal to each other, and they both have the value of RL over R plus 2L quantity. And with R1 equals R2, it's easy to see that B2 is 1/2. And since there's no connection from this network to the input voltage, V1 is 0. So V out to V in is A1 minus B1 divided by B2 minus A2. It's 2RL over R. Okay, well, that's not an output current, but notice here that V sub N is half of V out. And that's equal to V sub P, the non-inverting input voltage. And the non-inverting input voltage appears across the load resistor. So V sub P to V sub N is RL over R, and the current that's flowing in the load resistor is V in over R. And if the 4 resistors, R1 through R4, are matched, the current through the load resistor is independent of the load resistance. In fact, the load need not even be a resistance at all. I'll show you that in a moment. But before we move on, let me mention that the Howland Current Source is available as an LT Spice file as bonus circuit number 7. Okay, here's the Howland Current Source with a 1N4148 diode replacing the load resistor. And this plot shows the current in the diode versus the input voltage. It is linear, has a slope of 100 microamperes per volt, which is equal to the conductance of each of these 4 resistors. Now, one last thing, I want to show you what happens when we change the x-axis variable in the simulation to V sub P. We do that, and it produces a plot of the IV characteristic of the diode, an exponential characteristic that you're familiar with. There it is. Okay, so I appreciate your attention, this introduction to the BOAAT technique. There will be 2 more videos in this series. The next one, which will follow shortly, is applying the BOAAT technique to op-amp circuits that involve a capacitor. But so, to be continued. It has been my privilege to be your presenter, and we'll see you again soon in the next video.